But we are engineers. Every time you will have to look at it from an engineering perspective, right? When we derived this from a physical system, from a differential equation, you remember that S came because, why I say frequency shifting? That is because now this is a typical problem which is very easy to solve, and by now you would have guessed that the frequency shifting has to be applied because you have a cos function, a sine function which is being multiplied by e power minus 2t. But we are engineers. Every time you will have to look at it from an engineering perspective, right? So this means we proved that both sine and cosine, when we took the Laplace transforms, we interpreted that this is the solution of free vibration of spring mass system, right? The differential equation converted into an algebraic expression was the Laplace transform of sine and cosine, but now you have e power minus 2t. That means there is damping involved, because what it is doing is it is exponentially degrading the amplitude, rather decreasing the amplitude. That means you are also looking at damping along with the free vibration. That is cos is multiplied by e power minus 2t. That means this is going to form damped vibration. It's going to form damped vibration. But that apart, how you are going to solve this? It's very simple. Now the function is going to be rewritten as e power minus 2t. Of course, 2 as a constant can be taken out, cos 5t minus e power minus 2t into sine 5t, right? So you have got these two functions. Now, as I said, whenever you are solving this, you got to remember the formula for both cos and sine, and also remember the frequency shifting property. So what exactly I'm trying to say here? Because now you know that the S term appears in the numerator for cos, and only the A term appears in the numerator for sine. You should not miss, and I told you that is one error that most of the students commit. So what is the Laplace transform of cos 5t? It is very simple. It's going to be S divided by S square plus 5 square. Always remember, if you are talking about cos hyperbolic, a minus would come here. Because I am talking about only cos 5t, a plus comes here. Cos, remember S, that comes in the numerator. And whenever you have S term in the numerator, control engineers are not going to appreciate that. An incidental comment, we will discuss that as we get to the differential equations. Now you are going to have the Laplace transform for sine, and that's going to have only the A term in the numerator. That is going to have S square plus 5 square. S square plus 5 square is common to both sine and cosine. S appears in the numerator for cos, and phi appears for sine. So now, how exactly you are going to solve this? You have to apply the shifting property, right? So now you know the Laplace transform of both cosine and sine. Now how would you apply the shifting property? By shifting property, by frequency shifting, frequency shifting. Why I say frequency shifting? That is because yes here in Laplace transform represents the frequency. That frequency is actually increased or decreased depending on the coefficient of t in the exponential term. So now by frequency shifting, what happens here? Yes, for both the terms, since it is minus 2 and minus 2 for both the terms, S is going to be replaced by S of minus 2. That is, you are essentially subtracting the coefficient from S, and that leads to S plus 2. Okay, this is very important, and in future you would appreciate that this is positive damping. If this were minus, that would have been negative damping, but this is positive damping, right? So that is what exactly physically you will have to understand, that this is positive damping. And now if I replace s by 2 and s by 2, that is s replaced by s by 2, my solution is got. So what about my first term? It's going to be 2 as it is. Any constant should be kept as it is. Any constant should be kept as it is. And then e power minus 2t cos 5t is nothing but 2 into. So now that is going to be s is going to be replaced by s plus 2. And denominator also s is going to be replaced by s plus 2 plus 25 and minus sign as it is. And here it is just 5. So there is no s fortunately in the numerator, and there is no constant, there is only one term, and then here s is going to be replaced by s plus 2 and then of course 25. So this is the Laplace transform of f of t. If I call this f of t here, so this is the Laplace transform of f of t. Very simple, but you got to appreciate every time when you are taking the Laplace transform, the physical essence of the expression that you are dealing with. It is not just free vibration, it is damped because you have an exponential term. That's very important. And remember, these are the two standard formulae. For hyperbolic functions, it is minus here. For cos and sine, if they are not hyperbolic, plus. And for cos, s comes in the numerator. You are ending with s, so that comes in the numerator, and phi here. And also when we derived this from a physical system, from a differential equation, you remember that s came because your initial displacement was not 0. Remember, initial displacement was not 0, so therefore s into x of 0, remember s into x of 0, s survived. But here the initial displacement was 0, so s did not survive. Only the initial velocity was there, so you get a constant term. So therefore, if you correlate everything to physics, remembering also becomes very easy. And this was a very typical question. So no mathematical juggleries required here. Very straightforward. All that I did is frequency shifting. Remember, whenever you are multiplying a function by an exponential, if the exponential term has a negative coefficient, s is going to be replaced by s plus 2. I'm talking about negative, actual positive damping. And if it has plus, s is going to be replaced by s minus 2. When we finally construct the solutions and give you graphical intuitions, these things you would appreciate a lot. So the system response for various types of dampings. So this is the solution for you. So let's move on and look at more typical problems. So once we master these basic problems, then we can get into higher order learning in Laplace transforms. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.